Hello class, and welcome to COP 2334. So this is your instructor, Patrick Brooks. The previous videos were just kind of a copy of another course, Mr. Pinto's. The initial setup was done, and it was easiest to leave it that way, but from here out, the lectures will be recorded by me. So, what I'll do, how I'll do this, we have a new text for this fall 2021 section. And it is kind of a virtual text, whereas before we've had physical copies, and it's a double-edged sword. I like the new one because it's more concise. However, it does concisely convey the course material. You don't have to wade through, you don't have to you kind of wade, if you will, through pages of code samples, and if you get a 1,200-page text, it's kind of intimidating, anyways, right? So this one is it's bare bones. That's good, I think, right? And so what I'm going to be doing here in these lectures, I just kind of go through, and you see I have my little cheat sheet up here of things I want to talk about. What we'll do is we'll just kind of go through these one by one, and I'll briefly expand upon the topics. I'll give examples where, code examples where, where useful. They will be short. They will be brief examples. I think that's kind of the best way to go here. Keep it simple. You could extrapolate those out to, larger programs as long as you have the building blocks here. So, this course is C++. It's a third-generation programming language, meaning it's a high-level language. It's not machine language where you have to, actually type the instructions as each machine interprets them, or even assembly where you have to kind of type mnemonics that have a one-to-one, generally a one-to-one correspondence, with the exception of some macros, to a machine-level instruction, which is very tedious. Third generation and above languages are very powerful because one statement will perform many machine-level instructions. C++, regardless of what you might hear, you might tell somebody, hey, I'm studying C++, and they might tell you, oh, that's old stuff. Just ignore them, because, yeah, sure, they might tell you, hey, we're using, Python, Ruby, Scala, whatever, programming language du jour they might give you. That's great and all, and those languages have their place, and they're exceptionally useful in their own domains, but C++ is still around for a long time. If you really, most operating system code, the vast majority is in C. If you look at a Linux code base, it's in C. It's still maintained to this day in C code. It's very useful. C was developed in the late 60s by a guy by the name of Dennis Ritchie, who died several years ago. His death was kind of eclipsed by Steve Jobs' death, but he did contribute a lot to computer science. And C++ is really an extension of C. It's a superset of C. It was developed by a Swedish guy by the name of Jernis Trustrup, who used it for his thesis in school, and I believe it was 79, maybe 77, but I'm thinking 79. And basically, it contains the C language, adds a few extra things onto it with object orientation with classes. It was actually called originally C with classes. C++, the C++ name here came from the plus shortcut operator for incrementing onto variables, which we'll talk about. So it's a cute little pun anyways, on saying that it's, the next iteration of the C language. And C was derived from B, which is a prior programming language, and there were successors D and E, and so forth. If you really want to know about the history, I have a PowerPoint that is in the course materials. Go check it out. It's good to know where you came from, where you're going. If you take a programming language class, that kind of lays the foundation, the groundwork for it anyways. So I guess we'll start at the top. I kind of skipped toward the end, but I wanted to tell you, this is C++ and give you a tiny bit of background anyways. So ignore those naysayers. C++ is great and very useful and still relevant. So this is a programming class, obviously. We're going to be solving problems through computer programs. I guess what is a computer program? Well, the text will tell you input, process, and output. You provide input to a program. It processes that data or runs some other processes inside in the code, and it gives you output, right? It provides output. The process part we control as programmers, right? We write the code. Therefore, we are in charge of the process. We can take input and we provide output. Program really isn't much use without output of some sort, even if you're just displaying stuff for the end user. So this is pretty intuitive here. And I'll just give you a very small example of a program here. And we'll just use kind of the cliche one, hello world, that's always your first program. And I'll do some hocus pocus up here, which we'll talk about later. You can just ignore this for now. So what I'm doing is I'm just displaying hello world onto the console. So I'll click here, compile and link. You saw this in the environment video, setting up your environment, and then I'll run. There you go. So there's my output. I didn't provide any input. Input's obviously optional. Output, you can have a computer program without output here. This will still run. It just doesn't make much sense to have a computer program without any output whatsoever. There you go. An output can be, to the console, to a file, to a database, whatever. To a network interface to send to someone else, whatever. So that's kind of a very basic program here. And you notice I don't have any variables in here. What is a variable? Well, if you've taken at least pre-algebra, you know what a variable is. N, X. Those are some popular names for variables, right? Kind of to give you a kind of a very basic pre-algebra or algebra problem. There you go. X is your variable, and it's called variable because the value can vary. It just depends. In this case, we know that X is 6 because if we follow just the kind of the basic algorithm for solving this sort of equality, that you subtract the constant on the left, on the variable side, you subtract it from both sides. So in this case, 9 minus 3 would equal 6. So in this case, our variable is 6, but it could have been anything. What if I had this? There we go. What if I had this problem? X would equal 3. So that's why it's a variable. Its value can vary. It can represent an infinite number of things. And we'll see about variable declaration and usage very, very shortly within the next few minutes. You notice I use the term algorithm. An algorithm is a precise series of steps that we can use to solve a problem, or that we do use to solve a problem. I think I gave you the algorithm here, right? I don't know. You basically isolate everything on the non-variable side. You isolate the variable by itself, excuse me. So in this case, we would subtract 2 from both sides to eliminate this 2 here, and that would give us x equals 17. So there you go. It's kind of my algorithm, right? Isolate the variable by in this case, subtracting or adding to the value of the constant on the side with the variable in order to eliminate it. And there you go. It's x equals 17. So that's what an algorithm is. Algorithms can be very complex, or they can be very simple, like this one. Main. All right. So you see I have main here. Main is the entry point. This is a function name. A function is something that does something. Method, function, whatever. A function can take the input and provide output. So a function is kind of a logical grouping of code statements. It optionally accepts a value and optionally returns a value to you. So you can kind of think of that as input and output on a more micro scale than a whole program. Although I will tell you this, main represents that is the entry point to your program. So every computer program is going to start with main. If I, package this up and call the executable, it is going to start with main, by double-clicking on it or whatever, however you want to call the executable. Usually double-clicking on it if you don't have, experience in the computer science world is, kind of how you can think of as executing a program. Double-click on it, it'll start at main. That is the entry point to any program. So, if I can create a whole computer program, and we're going to start right here on this line 26. If I, execute this one. And I can add, all kinds of statements here too. It doesn't matter. It's going to start right here. Notice my statement did end with a semicolon here. So I said, hey, go ahead and take hello world. You see the arrows. This is my output stream, my character output stream. C out, character out. This is my character output stream. And you can put more than just characters. This is an example of a string. It's a character string, but I can put more than just characters into the output stream for display, and we'll see that in a sec. So look at it this way. I'm taking the string, the character string hello world. I'm pushing it. You see the direction of the arrows to the left. I'm pushing it to the character output stream. And so that is why we get the hello world. Where is it? Yeah, there we go. That's why we get the hello world in the character output stream. In this case, it's in the console down here at the bottom, but if I ran it, from the command line, I'd see it here in the command line. So the statement has to end in a semicolon. If it doesn't, wow, it tells me no, dummy, you got to put a semicolon before this brace here. So this one was some error messages you get are a little bit kind of obfuscate. They obfuscate the real problem, but this one's pretty easy. It says, hey, put a semicolon there, dummy, you forgot it. And anything, if we go on, see about data types. We'll go ahead and just give you an example of a data type, integer data type. This is a statement. I've declared a variable named x of the type integer, and I've assigned it the value 6. All right, so we'll start over here on the right-hand side, value 6. That's pretty obvious. That's a constant value. It's 6. It's not a variable. Notice my assignment goes from the right to the left. So I'm taking this constant value 6, putting it into the variable x, which is of type integer. We have several data types in C++. One of the data types here is integer. And if you don't know, an integer is not just a counting number, but you can think of it as a whole number, right? A whole number, be it negative, 0, or positive. So that's going to be an integer. Basically a number without a decimal point on it is how you can think of it, positive or negative or 0. Okay? So that's what an integer is. We have several data types available to us in C++, several primitives, which means non-objects, which we'll cover later in the class. So I could say I'll have a double y. Actually, you know what? Here. Float. We'll start from the ground up. Floating point. That is going to be an integer that allows for decimal at the end, what we call a mantissa to the right of the decimal point. So that's going to be, you can think of it as an integer with more precision. It's a floating point number. 3.5 could be an example of a float, or 9 point, whatever, right? So that is an example of a floating point value. We also have double, which is a double precision floating point value. It was originally intended to have more precision than float, meaning you could specify more numbers in there, right? We could have a larger number. We could also have more precise number. Generally, the compiler treats them the same. Depends on on your system, but that was the original intent. And we'll cover a few of these. We'll save some more complex ones for later. We could also have a character data type. There we go. So in this case, I made my character see a value, the character literal capital A. Okay, sorry, I had to step away for a second. All right, so we have integer, float, and double. We also have a character literal. Note how we have to denote a character literal. If I try to come in here and say, hey, I want a character literal that's A, no. Syntax error, and we'll talk about that in a sec. But we have to wrap our character in single quotes. Character can only be a single, right? We aren't dealing yet with strings of characters like we have here in the string literal. We'll talk about string literals in a later chapter. So yeah, A doesn't work, A does. Now, don't get confused. If I try double quotes, that is a character string notation, and it doesn't like that. You see what it's trying to tell me is, hey, it's saying, hey, dummy, you're trying to take a character and use string notation for it. That's a character pointer, which is kind of another way of saying string, basically. Just tell me, hey, dummy, you did a wrong thing there. Yep, oops, there we go. All right. I can display all of these, right? I don't you see the output stream accepts more than just characters, so I could say X, Y, Z. I could display all of these, and this will get a bit jumbled. But say, hey, display C, Z, Y, and X to the output stream, and we're actually going from left to right, so it'll display X and then Y and then Z and then C. All right, you see I'm chaining these together so that I can display several variables in a row. All right, oh my God, we have 6, 3.5, 2.343a. So that's a problem. What I can do, I can also, so we can kind of mix. We can mix variables and string literals in here. So you see what I'm doing? I'm displaying X and then a space. That's a string. And then Y and then a space. And then Z and then a space. And then C. So now we should see 6, 3.5, 2.343, and A kind of more legibly here. There we go. All right. That's just example of return types. Okay, return, or data types, excuse me, return. All right, we can return a value from a function. If we don't specify one, then, okay, well, I'll back up a minute. So here before, this is the function name is main, right? Remember I said that was kind of the principal function, that's the entry point to a program, is the main function. This is the return type. This is the data type that the function will return. In this case, main is a special function. It'll always return an integer. And it will return, and I'll put a comment here, and I'll talk about that in just a minute. It will return 0 by default unless you specify a particular return code. If I want to create some sort of error condition, I will specify a non-zero return code. For main, that means that the application returned an error. It's a special function. 0 is normal, 1 is abnormal, meaning something occurred. Let's say, X has to be 5, and we'll see conditional logic, so don't let this kind of throw you for a loop. Just take it that this basically says, hey, if X doesn't equal 5, then we'll return 1. So that way the caller, the person who invokes, who kind of calls this program, will know that an error happened. We could also change this to say, I don't know, we could say, hey, if Y doesn't equal 3.3, then return some other value. So you see, we can return different values indicating different error codes. And in fact, if you look at Linux, you have, this is called errno, and you have, tons of different values you can return, basically saying different things. File couldn't be read, improper permissions, not enough memory, etc. So just know that we can return values from functions. We specify the return type before the function name, and we'll go over this when we get to functions. Don't sweat too much about this. And main is a special function that will return 0 if everything went okay, or a non-zero if stuff happened, if bad stuff happened, indicating some sort of exception condition, some sort of bad condition, error condition. All right, so we got return. Yeah, so here we go, cout, so character output stream. We're pushing this string literal hello world into the character output stream. Or, we have this chain, right? X followed by the value of the variable X. Oh, so the variable X is just a handle, right? The computer stores X into a memory location that it knows that's numeric. And from then on, we have a handle to it, and we refer to it as X. Thank God we don't have to know the memory address and write the memory address each time. That would just, that would make programming extremely unproductive, as we would have to manage all of this. So it's a lot easier for us to think in terms of abstractions. X, we just refer to that handle X. Thank God, right? So we're displaying the value of the variable, the value of the memory location associated with the variable X, which I'll just refer to as the value of X. That's easier to think of that way, followed by a string consisting of a space character, basically a space. Followed by the value of y, and then a space, value z, a space, and then c. Now, we can also take stuff in. Watch this. I can accept any value. Oops. I can accept any value using the input operator here. Here. I'll read in C from the keyboard. And it's kind of useful. It's more useful to prompt, right, the user and let them know I want a character. Otherwise, you'll just get a blank cursor and you won't know what to do. So I'll say, hey, enter new value for C. And then we'll display, we'll just kind of copy and paste this. Then we'll display everything again, and we should see our new value of C there, because variables we can overwrite. It's just a variable, right? As such, we can change it. Oops. Oh, hey, let's see, what do we have? Go to the top one. All right, no match for operator. Duh. Sorry. We can. This is the. So we have the extraction operator and the input operator. Sorry, I got them backwards. So when we use cout, you know, we are pushing X into the output stream, which is, you know, the console or the you know, the command window. And here we're reading from the character input stream. We're pushing it. Note the way the directional arrows go into the variable C. All right. So now that should be clear, let's go ahead and run this. There we go. 6, 3.5, 2.343, an A. And I'll go ahead and deal with this. You see this sloppiness here. I'll deal with this in a sec. We'll go over something else. Enter new value for C. I'll give it the value T. There we go. 6, 3.5. Oops, I accidentally put backslash. 6, 3.5, 2.343, and T. All right. And you know, I can read in anything I want. You know, we'll run this again. Here's an interesting new value for C. Well, what if I put 8 there? Is that going to be a problem? The answer is no. You know, look at your keyboard. 8 is a character value, right? Anything on your keyboard can be interpreted as a character value. If you explicitly specify that it is an integer, it will be looking for some sort of numeric character, right? However, I can enter anything I want for C, including a number. And I can also, you know, like I said, you can see in any data type. Then I'll repeat this guy. So just kind of show you. All right, new value for C. We'll say R, and all right, good. Oh, I forgot to put the cout statement here, prompting that I was looking for a new value for X. But anyways, I'll enter the new value for X now. I'll say it's 7. And look at that, 7, 3.5, 2.343R. So let's deal with this. Let's deal with this ugliness here. You know, hello world, and then we have some stuff that kind of butts up to it, is very adjacent. Right here, juxtapositioned here to it. And so what I'll do, hello world, I can specify that I want to end the line here. Oops. Darn. There we go. So that tells ENDL, tells C++, insert a new line here. This is the end of the line. Now, watch, I should see a space, or I should see a line after hello world. There we go, look at that. All right. We forgot to do it here. And this one I'll do a different way. This one, you see what it did here? You might think that it's going to display \n, but watch what happens. Oh, yeah, sorry. I put it in the wrong place. Hey, how about that? So \n, the backslash is what we call an escape character. And it says, hey, I want to do some fancy mumbo jumbo here. What follows that dictates what that fancy special sauce is. Backslash n just basically says new line. Insert a new line into the output stream. Basically, go ahead and end the line here and go to the next line. We have some, backslash t is to put a tab in there, and there are several others, but just know that is an alternative to endl is backslash. If we put backslash n character into the output stream, and we could put this here. We could put it in as part of the string. It's a character, right? It's a character in a bigger character string. So in this case, we'll have two new lines after n world or hello world because I have a backslash n and then I have an endl. Watch this. Oops. Yeah. There we go. See, we have two lines, one and then two. All right, comments. You want to document your code. Good code is self-documenting. We shouldn't have to ask what the code is doing, but sometimes, when you do, you don't want to overload your code with what we call comments. However, we do want to make it clear what's going on in some places. Particularly, you don't want to comment, let's say every line of code. We used to hear that in school, comment every line of code. Oh God, that's garbage. No, don't do that. That's just annoying. However, you could do this a lot before functions, on top of functions. You can create Java docs in Java, whatever. But here you can create a comment saying what the function does, or if there's a particular part of the function you think kind of isn't too clear as to what you're doing, you can't really make it very obvious, then you could put a comment there. Now, watch this. If I come in here and I say, I don't know, it is an annoying comment, right? Because it's obvious, it's already Captain Obvious. I'll say, prompt user, no, you know what? Display cliche line in program. It doesn't do anything. It's a comment, so it's not executed. It's only there for documentation purposes in the source code. I could also put that here at the end of the line. Basically, this is a single line comment, so anything after the two slashes, the two slashes here against each other, anything after this is not executed. So in this case, hello world will be executed. However, it stops here on this line. It would start again execution of the next line. We could, if we have a whole bunch of stuff, we could say, display X, Y, Z, 1, 2, 3, 4, and then say we run out of room on the line or something. Then display blah 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 blah. Sure, you could have several multi-line comments, but an easier thing to do might be what I did up here. And you may have already asked yourself why the compiler didn't gripe at me because I had 21 lines of junk up here. You see the slash asterisk? That is the start of a multi-line comment. And over here, asterisk slash is the end of the multi-line comment. So anywhere the compiler sees slash asterisk, it says, oh, don't execute this stuff until after the closing slash asterisk. So that's what, you can actually see the stuff's in orange, right? And that's called a multi-line comment. All right. Indentation. Readability is key. People will come behind you and maintain your code, perhaps years later after you've been gone. If you go to hopefully a higher paying job, if you get hit by a bus, that's not going to happen to any of you. We'll think positively here. Or even if you come, you'll come back and look at your own stuff and you'll say, what was I thinking? What was I doing? It'll look like a stranger's work. I promise to you. I promise this to you. You can come back a couple of months and it'll look like a stranger's work. So, the comment thing, that's one thing, but readability is key. If I do this, I have my curly braces here, which is the code block. But let's say we have some nested stuff in here. If, I don't know, if, And we're getting, yeah, where we haven't covered this yet, but you'll kind of get it. If x is equal to 5, then do this stuff. Oh man, so now I can't tell what sits where, what logic is appropriate to only the, the inner, what we call block here, basically the inner curly braces. This is a nightmare. Don't do this. What you want to do, and we'll talk about this, as we get into blocks, but what we want to do for now, know that you have to indent your code within the same, within the same block, within the same parenthesis, curly braces should be appropriately indented at the same level. I have 2 spaces here, right? So I want to keep everything at the 2 space level. And then if I have a, some sort of nested statement, guess what? I want to indent in there, and then everything in here, would be at the same level. And in fact, if we had, I think it was mentioned earlier in a generate CSD, hey, look at this, we can see my different levels and kind of indents for me, so that's great. For now, just obey this, please. Don't send me stuff, in multiple blocks in the same level, no indentation. I'll just send it right back to you. All right, white space. Yeah, white space is big, right? If we start stringing things together like this, it becomes impossible to read, debug, and maintain. This will compile because we have the semicolons at the correct place. This junk will compile, and no one can read it or maintain it. Yeah, so when you get a bad error, we saw earlier, let me go back up here. What did I have? Yeah, you see I have a whole bunch of stuff. Oh my God, what is all this? Oh my God. Well, this is templating and stuff, but anyways, if you look at this, it's like, what in the world? Oh, 10. Oh, how many do we have? Like 20, 30. Oh God, I don't even know. So what's the problem? Well, if you come up to the top, what you want to do is start there. You stuff cascades from the top. If you're reading stack traces in Java, you want to go to the bottom because that's generally the caused by. But here, you want to go to the top thing that went wrong. Here it is, right here. No match for the input operator when I should have actually been sending. I should have been sending the result of the input stream to, I had the direction backwards. Obviously, the arrow should be pointing to the right, to the variable C, to the value. I should push that into the value of the memory address associated with a variable C. So you see, if I come up to the top and fix this, it's a whole lot easier. It kind of clears everything up. So yeah, start at the top, and then you won't get as much cascading. Or maybe that's the only error, right? So always do that. Start at the very top. Syntax. So this is an example of a syntax error. It says, dummy, you put C in here, and you're using the extraction operator. No. You want to use the insertion operator. You want those arrows to be pointing to the right. So that was an obvious dummy mistake. I kind of didn't adhere to language standards. But let's say that I want to, here, you know what, we'll do this. Give me a number and I will square it. Then we'll, you know what, every statement ends in a semicolon. All right, so I'll take the number and I'll say, I need to declare an integer first, and then I'll accept it as input. And I'll say, hey, give me this number squared. So this should be a correct program, right? Give me a number. Oh, I said 6. All right, so let's do this. Oh no. Obviously, the asterisk is the multiplication operator. Multiplication, division, addition, subtraction, easy stuff. Anyways, so I'll say, hey, give me, put into the output stream the result of the variable x times the variable x, obviously the value of the variable x times the value of the variable x. So yeah, give me a number and I'll square it. I'll give it 8, so it should be 64. That was an X in the input stream. Sorry. There we go. 8, 64. All right. But what if I do this? My son did this the other day. An accident on. Okay, sorry, I had to step away for a sec. Oh, yeah. Also, feel free to step away, right, if you need to. These I'll keep these manageable. They'll generally be under 45 minutes. But if you need to step away, as you see fit. If you feel overwhelmed, you need to go back, kind of get some water, go for a walk, whatever you do to kind of clear your head. That's great too. So let's see. So we were at C. Haha, yes. So if I do this and yeah, so I'll square it. 8 is 64. So that's all fine and well, right? But what if I were to do this? All right, yeah, x times x. Oops. My son did this in his homework the other day. He was using pluses instead of asterisks, or instead of times. And you generally don't see the problem in your own work, but, fine, it happens. So let's say you do this instead. Well, 8 squared is not 16. That is a logic error. The compiler didn't catch it, so it is a logic error and not a syntax error. PowerPoint for code. So we're compiling and linking here. What does that mean? Well, so there are a few steps: pre-processing, compilation, linking. You have intermediate, output files. You have assembly machine. Anyways, if you're interested, go into that PowerPoint and check it out. I'm not going to force this on you, but you can kind of see some examples. It's actually really, really interesting how this all works behind the scenes. This is von Neumann architecture. Basically, what we're saying is that there's a hierarchy, goes from cheaper to more expensive as we go over to the right, and your axis also gets from slower to more to faster on the right. Tertiary storage is offsite storage. So if you have like backup tapes, the company has backup tapes at an offsite location. It takes a long time, right? You got to retrieve them, you got to bring them in, you got to kind of pull them into the machine. So it takes a long time to get your backups from tertiary storage, which might be, like I said, tape drives or something, tape archives on an offsite location. Now here, these are things that we see on a computer. We see disk. We also have RAM, which are those memory modules you plug into your motherboard there on your machine. And then we have CPU cache, which they're actually kind of is a cache, which can be expressed in kilobytes or even megabytes on your actual memory, your CPU. It's a little tiny area of your CPU that it can retrieve memory quickly. So kind of you can think of it as this way. The disk is on the machine, that spinning magnetic disk, or a really solid state drive for a lot of newer computers. You probably have more. I haven't read, I've been involved in software stuff lately, but so I haven't checked stats, but I'm willing to bet by now you see as much or more SSD of the SSD solid state drives than you do the old spinning. I say old, the spinning magnetic disks. So disk access takes several cycles at least. You gotta request the info. You have to wait for the disk to rotate around to to where it's in the proper location for you to read from that memory sector and block. And also you have your seek latency, right? The read-write head has to go to that actual track where that data sits. So add all those up. It takes a while. It takes a while to get data from disk compared to RAM, which is you just kind of have a strobe. You send it down and say, hey, I need this row and column location to kind of simplify it anyways. And it's returned back to your RAM is a lot quicker than disk access, orders of magnitude quicker. And then you have your CPU cache, which is immediately available within one cycle generally. To us. CPU cache is, you have, variables, things are cached. If you read, there's temporal and spatial cache. So if you read something in, if I read a variable in, let's say X, I'm going to use it pretty quickly. If I access it once, I'm probably going to access it again in the very near future. So that's the thought here. That's why we have cache. That's locality, it's temporal reference. And then beyond that, we have locality of reference. So if I have an int X and also have an int Y adjacent to it, if I access X, I'm also, chances are, since it's next to it, I'm also going to access Y. So we have cache lines, and a cache basically reads in a whole cache line, which is like a contiguous block of memory. So in this case, if I read an X, I'll also have Y in my cache line. So I'll have Y available to me pretty much instantaneously. The way you can think of this, disk, and they really are orders of magnitude different. Disk, if you get data from disk, you're going to have to grow potatoes in Iowa, is it Idaho? Yeah, Idaho, sorry, duh. My wife would kill me for that. She's from Midwest. You grow potatoes in Idaho. That's really how slow disk access can be compared to RAM. RAM is, let's say the potato chips are in a bag in your cupboard. You open them, you put them in a bowl, and there you go. You have your potato chips. In this case, CPU cache would be like you have the bowl in your hands, and all you have to do is kind of grab a chip and put it to your mouth. So that's how that's the orders of. That's how large the differences are here in the memory hierarchy, von Neumann architecture. Storage hierarchy. A bit is a single, it's a 0 or a 1. 0, 1, that's it. Bit, binary digit, B-I-T, binary digit. Byte is a series of 8 bits. There's an example of a byte. Something that might correspond to a byte is a character. If we come over here to ASCII table, we can see that we have our standard ASCII goes up to 127, then we have our extended ASCII goes up to 255, and that can be represented with 256 different values, which is also how many values we can represent from a single byte. You have 127. You have you kind of have weighted positional notation here, but basically they all add up to anywhere between 0 and 255 for a single byte. So that's how many combinations of zeros and ones we can come up with to get a unique value for a byte. So you have a bit, and then you have a byte, which is a string, a series of 8 bits. Then you have kilobyte, which is approximately, a lot of people say it's 1,000 bytes. It's not. It's actually 2 to the 10th. It's 1,024 bytes. Why? Well, it's binary. 2 to the 10th. 0 or 1, so it's approximately 1,000, right? So a kilobyte is 1,024 bytes. A megabyte is what? 1,048,576 bytes. In other words, 1,024 kilobytes, and so forth. Giga, tera, peta, exa, zeta, yada. You see stuff up to exabytes, when you're talking about traffic going across the internet. I haven't really seen too much stuff that deals with zetta and yada, too many figures, but I imagine that, before long we will. Moore's Law. Moore's Law basically says that, mention is made of it in the text between, every 18 to 24 months, and it's held constant since 1985, I believe, is when this kind of came about. 18 to 24 months, processor speed doubles. When we got when we got our household Dell computer in the early mid 90s, I think it was 25 megahertz was the processor speed, and that's about par for the course. You see them climb pretty quickly, right? You'd buy a video game and almost need a new computer, really, if you were at the cusp of gaming. I haven't gamed in many years, but that was the case, and it's because of Moore's Law. We're always kind of packing more transistors in there, increasing CPU speed. Now, we did hit a power wall some years ago. With the time it was in the threes, you could see, and that probably still is the case, I'm sure. You don't, again, I do more software stuff than hardware nowadays, but you really didn't see much more than 3 X megahertz or million cycles per second, and it's because you get too hot. The processor, you need a lot of cooling, and if you get a processor too hot via too many cycles, then it will, you can exceed the chip junction temperature threshold, and so you can actually damage the chip. So how we dealt with that, Moore's Law still applies, but we kind of scaled horizontally. So we added processors instead of just making processors, quicker. And so we have multi-processing. So basically we have, overhead and coordination of a whole bunch of processors, a whole bunch of cores within a single processor instead of just making the processor, give it more cycles per second. So that's how we got around Moore's Law. And I wanted to touch a little bit on Moore's Law. Moore's Law basically says that, no matter how quick we make, how powerful we make computers, developers will still use all that stuff. Right, like I said, gaming is a good example. We're always taking examples of, hotter GPUs and processing power, etc. If you're at the cusp of gaming, you're going to have a by necessity a really, really hot machine, right? So that's Moore's Law for you. We're basically using everything that we can develop. And Pareto principle basically says that 80% of your users are going to only get to use 20% of the features of any particular software. So it kind of goes hand in hand with these other two. Efficiency still rules. Efficiency is still very important. You might be tempted to say, hey, machines are really powerful and have a lot of RAM. You still can't be sloppy with their programming. If you're interested in the C++ history, I touched on it a little bit earlier. You can just check out the PowerPoint. I have a PowerPoint out there. It's interesting. It's nice to know where you come from, where you're going. The history. If you take a programming languages, comparative programming languages course, a lot of that's you're gonna see that in there. And you're entering a very precision-oriented field, a very detail-oriented field. As an example, I like to use in 1962 NASA. They were using a computed guidance system for their rocket, and somebody left out here. Actually, it's right here. See the little hyphen here called a bar. Somebody left that out of the program inadvertently. It was a logic error, not a syntax error. It's still compiled. And basically, the bar, I think, if I'm not mistaken, it told the computer to ignore. Yeah, it basically said to ignore guidance under certain conditions. However, the absence of the bar sent the rocket in an errant direction, and they had to remote detonate it so that it wouldn't, fall on houses and kill people or whatever. But the point is, hey, a single bar caused millions of dollars there, in cost to NASA. So just keep in mind, kind of like the real estate maxim is what location. In programming, it's check your work. So I guess that kind of wraps up this chapter. This is kind of good for the first 2 weeks here. If you have any questions, let me know. Otherwise, I will see you at the next lecture. Thanks.